All right, folks, let's take a look at the binomial distribution. And the binomial distribution is based on Bernoulli trials. We talked about Bernoulli trials where we have a potential outcome of either 0 or 1, where 0 is something doesn't happen and 1 is something does happen. We call it a probability of success. So if X is a Bernoulli random variable, we look at a Bernoulli trial. And say the trial is me taking a foul shot in a basketball court. So I've got the basketball, I'm up at the foul line, I take a shot and I miss it. So that means it's not a success, right? It didn't happen, I didn't make that goal. So that is a 0, X is 0. If I come up to the line and make that shot, then X equals 1, it was a success. So underlying that Bernoulli trial is as a probability. What's my probability of making a foul shot? Say it's 50%. So if we look at taking a series of foul shots or a series of Bernoulli trials, then the probability of making, say, 5 shots out of 10, it follows a binomial distribution. So in this case, for Bernoulli, our random variable is X, and this is a binary outcome, right? Success or failure. For each trial, X can just take on 2 values, 0 or 1. In this case, Y is the binomial distribution variable, the random variable here. So the number of successes out of n trials, right? Now, let's just take a look at what this distribution kind of looks like. So say this is Y and this is P of X, it's discrete, right? Y could take on a number of values. I could make no foul shots, I could make 1, all the way up to say we're n is equal to 10, right? And well, I won't draw all those out. But underlying this is some probability of making 0 shots, some probability of making 1. Maybe I peak at 2, I don't know. That's exactly what it looks like, right? And so forth. So it's a discrete distribution because Y, in this case, Y is our binomial random variable, can only take on discrete numbers. I can't make half a shot, right? I can't have half of a success. So the parameters for this are n, we have to put in n, so how many trials are we looking at? And then we can find the probabilities of a given number of successes, less than, say less than 5 shots or more than 5 shots, etc. So that's what the binomial distribution is. Let's look at how we get to the actual PDF. So let's consider the number of cars approaching a stoplight. And we will, so this is the Bernoulli trial here is, does the car make it through the stoplight or not? Stoplight is gonna be green for so many minutes, and we have an underlying probability related to that time of being able to make it to the intersection. So we don't know when I'm approaching it in that cycle, and there's a certain probability that I'll make it through. So let's say that X is equal to 1 for this Bernoulli trial. If we pass through the stoplight. And the probability that X is equal to 1 is equal to some probability. We don't need to define it now, but say my probability at any given point coming to this intersection is 75%. It's a pretty long green light. X is equal to 0 if we are stopped, right? We get that red light, or yellow. We slow down and stop if we see that, okay? Now, let's think about repeating this for 3 cars approaching the stoplight. Okay, and so this is really 3 trials, right? Each time a car comes, that's a trial. So we say n is equal to 3 trials. Let's take a look at how Y behaves. So, and sorry, let me just define this. So we said that the probability that X equals 1, that we have a success as P, the probability that x equals 0, that we're stopped, has the complement of that, just 1 minus p. Okay, so we just have two possible outcomes. Probability that a success happens is p. The probability that success doesn't happen is its complement, 1 minus p. So if we do 3 trials, we observe 3 cars approaching. Now our new random variable y is equal to the number of successes out of 3 trials, or n. All right, so here's a table showing the potential outcomes we can have. Trial 1 is that first car approaching, right? And we could have that car not go through or go through, right? And so let's look at all the potential outcomes for y. So we could have 0 cars passing through out of 3 trials, 1, 2, or 3 cars, right? But there's different ways that could happen. So how many different ways could we have 0 cars passing through out of 3 trials? Well, there's only one way that could happen, right? So we have 0 in the first trial, and that has a probability of 1 minus p, 0 in the second trial, 1 minus p, and 0 in the third trial with 1 minus p. Okay, makes sense, right? We're following so far. So each of these independent trials has a probability of 1 minus p of happening, and we only have one way of having 0 cars pass through. Now, what about 1 car passing through? Well, there's a lot of ways this could happen. We could have, in trial 1, the first car passes through with a probability of p, and then we'd have to have 0, right, with 1 minus p probability. Or we could have 0 in the first trial, 1 in the second trial, and 0 in the third trial. Finally, we could have 0 in the first trial with a probability of 1 minus p, 0 in the second trial, and then 1 in the last trial. So each of these combinations result in 1 car passing through, or 1 success out of 3 trials. And we have 3 combinations, or 3 ways to do that. And so I'll just write out the rest for 2. All right, so we have 3 different ways that 2 cars could pass through out of 3 trials. And then finally, we only have one way with a probability of p each time that we could have 3 cars passing through. So this table shows us all the different combinations for each of these potential outcomes for y. Now let's write this out using our probability symbology. If y is the number of successes over n trials, the probability that y is equal to 0 is equal to the probability that we have 0 in trial 1, so I'll write it as a subscript, and 0 in trial 2, and 0 in trial 3. So because these are independent, right, or at least that's the assumption we're making, then when we do this event and this event and this event and all at the same time, then we can just multiply those out together. So there's no conditional probability here. So this is the probability of 0 for trial 1 times the probability of 0 for trial 2 times the probability of 0 for trial 3. Now let's write those actual probabilities out. 1 minus p times 1 minus p times 1 minus p. And so we get 1 minus p to the 3rd power. Similarly, let's look at the probability that y is equal to 1. A little more complicated, but we get, but we're going to do the same pattern, right? So we can get the probability that we have a success, that x is equal to 1 in the first trial, and 0 in the second trial, and 0 in the third trial. Or we could get the probability that we get 0 in the first trial, 1 in the second trial, and 0 in the third trial. Or we get the probability that we get 0 in the first trial, and 0 in the second trial, and 1 in the third trial. So just a little more, those are the three combinations, right? We can plug in our probability values here, and we'll note that all of these are mutually exclusive, right? Because we only have one outcome. These are three different ways that this outcome could occur, but we can't have one in the first trial and one in the second trial, right? So these are all mutually exclusive. These can't happen simultaneously. So because they're mutually exclusive, we can just add these up, right? We can multiply within here and then add them across the different combinations. So here we get the probability that we have 1 in the first trial times the probability 0 in the second trial, plus, and I'll just write these out. Sorry, that's a 1 in the last trial. All right. And then we can actually plug the probabilities here. We get p times 1 minus p times 1 minus p. So here's 1 in the first trial, 0 in the second trial, 0 in the third trial. All right, so these are all the probabilities of these three different things, and we're going to add them up. And so we end up with 3p times 1 minus p squared. So we're just adding these all up. These are actually the same things that we're just adding up 3 times. So we'll do the same thing for y equals 2. And this is equal to, ends up being 3p squared, right? Because we have 2 successes times 1 minus p. And the probability that y is equal to 3 is just p cubed. So we get a pattern here, right? We see kind of when 1, we have a 1p here, and we have 2 of these 1 minus p's. When equals 2, we have 2 of these p's multiplied together, and just 1 of these 1 minus p's, etc. So we see a pattern developing. So if you formalize this and then make it more general, then we can say for n Bernoulli trials, which are binary outcomes, remember, with a probability of success p of 1 trial, right, within each of those Bernoulli trials, and with y is equal to the total number of successes over n trials, then the probability of y successes follows this binomial distribution. And so what we end up with is n radical over y radical times n minus y radical. And we'll talk about this factor right here in a second. P to the y, 1 minus p to the n minus y. So this is our binomial distribution right here. Now let's talk about what this factor is for a second. And what this factor shows us, or calculates for us, is the total number of combinations. How many ways can we have 1 success out of 3 trials, right? Or 2 successes out of 3 trials, etc. So this is what calculates that for us. And we can also write that factor as n choose y. So that's another way to notate it. It's just the same thing. It means the same thing as that. And then our calculator, we can write it as NCR. That's, at least in my calculator, this is what the button is. And so we plug in the number of trials. So say in this case, we do 3 trials. Then I press that button NCR. It's under probability in my calculator. And then I put in the number of successes. And so say I want to do 2, right? And so that'll give me the number of combinations, number of possible combos, right? How many combinations can we have? How many ways can we have 2 successes out of 3 trials? So that's how we calculate that. You don't have to do this by hand, right? Radical would be, for 3, it'd be 3 times 2 times 1, and that's kind of a pain to type in, right? So it's not too hard to do this distribution in your calculator. And we can also do this calculation in R using the D binomial function. And so for D binomial, we plug in the following. We plug in Y, so the number of successes we're interested in, N, and P. So P is the underlying probability, right? This is N is the number of trials, and Y is the number of successes we're interested in. So the probability that Y is equal to some value, so number of success, is equal to this. So it gives you the actual probability. Because this is a probability mass function, it's a discrete random variable. If you use the density function for binomial, it will output a probability value. We also have p-bin, which will give you a cumulative probability, right? And let me just write out the cumulative probability distribution functions. Now the CDF for the binomial distribution is really just summing up that PDF or that PMF, right? Because it's discrete. So if we write big F of Y, that's our CDF, right? This is equal to the probability that Y is less than or equal to, we'll say K successes. So remember, it's the cumulative probability. So we're going from 0 all the way up to K. And that's going to be equal to the sum from 0 to K. K is equal to 0, right? Of that PDF or that PMF. So N trials, K successes. So N choose K. That's the number of combinations we could have for each. P to the K, 1 minus P to the N minus K. So now we're just saying, okay, we start at 0, we go to 1, 2, 3, all the way up to the number of successes we wanted. And so we're just adding up the individual values. So for our example, or the number of cars passing through. And then we would get our CDF. And so that's going to be a step function, right? So this is the PMF, and this is our CDF. Start at 0, 1, 2, and 3. And then we end at 1, right? So cumulative probability all the way up to 1.